In Chapter 6 of my Computational Linear Algebra book, we learn how to parallelize the various routines that we looked at earlier in the class for solving linear systems, linear least squares, eigenvalue problem, linear programming, and making them run efficiently on a multiprocessor machine. Well, you can think of a multiprocessor machine as consisting of a number of separate computers with their own memory, or at least their own section of memory, but with the ability to communicate between each other. And it's important to minimize the amount of communication between the processors because that's very slow compared to the internal work on the processor. So if you want to run any program efficiently on a multiprocessor machine, you need to minimize the amount of communication. Now, the communication in our Fortran programs is going to be done through MPI routines, and basically all of the routines in this chapter get by with only two basic communicating routines. There's the MPI bcast, which broadcasts a message to all the other processors. So let's look, and here's the other one. Let's look at MPI bcast. There's a special processor for this one, JTask. That's the number of tasks that is going to broadcast, and it will broadcast its vector x of length n to all the others. So everybody calls MPI broadcast, and this special processor number JTask, its x will be passed on to everybody. So after this call, everybody has the same vector x of length n. The other routine is even more useful in our routines, MPI all reduce. And this takes everybody inputs their xi, and they're all added together, and everybody gets back the sum of all of them. And xi and x can be scalars, or they can be a vector of length n, generally a vector of length n, and you do it component by component. But if n is 1, then basically everybody just puts in their value of xi, and everybody gets back the sum of all of them. At least if this parameter is MPI sum, it can also be MPI max or MPI min, in which case the x will be the minimum. The first component of x will be the minimum of everybody's first component of xi. The second component of x will be the minimum of all components of xi. So they're done component by component, if this is a vector, and they'll either sum them or take a minimum or max, and there's some other operations, but those are the only ones we're interested in. In fact, we're nearly always going to be taking the sum, so this will nearly always be MPI underscore sum, in which case everybody puts in their xi vector, and they're all added together, and everybody gets back the x. In these two routines, you can do most anything we need to do. Well, you've already seen a parallel Fortran program back in Chapter 4. Remember, in pricing options, we said, well, why not just do the experiment here? We claimed that we could that a log normal probability distribution is what you'd get if you flipped a coin a whole bunch of times, and price went up by a factor of r if it were heads, and went down by a factor of r if it were tails, and flip a bunch of coins and actually see what the future price was. Well, we can actually do that experiment, a Monte Carlo experiment here. You could take, in this example, we started out with an asset price of 39 and a strike price of 40, and we said, well, let's just flip 1,000 coins. Every coin flip, which we do with a random number generator, of course, price goes up or down by this factor RE, which is related to the dt, the time step, and the volatility. The bigger the volatility, the bigger step you take every step. Bigger R is, the bigger factor you change by every time step. In any case, you just do the experiment, and at the end you say, okay, here's the final price this time. how much did we make, and if S is bigger than the strike price, that's a call option, then you made a profit of S minus E. If it's less, you just don't exercise the option and you get 0. And then you do 10 million trials and you average all of those, and that should give you a pretty good expected value for your payoff from buying the option. But this is a type of calculation that's really suited for parallel processing, because instead of one processor doing 10 million trials, why not have 10 processors doing 1 million trials each? And they don't need to communicate at all. They can just do their million trials, and at the end they get together and average their averages, and that's the only communication. That's the ideal case. So let's look at this program. It's pretty simple. Unfortunately, our linear system solvers and so forth aren't going to quite be this efficient, because you have to do more message passing, more communication, which slows things down. But this one, you don't have to do any communication till the end. So let's look at this program. So basically, each processor is going to run exactly the same code. So how is it they do things differently? Well, you've got these calls at the beginning. This is just initialization that you always call. Everybody calls this routine here and asks, how many processors are we? And then this is the key here. Then you call com rank and say, well, which processor am I? And everybody gets back a different value of iTask. If there are 10 processors, one processor will get iTask will be 0, another one will be 1 up through 9. So the processor numbers are 0 up through NPES minus 1. So if there are 10 processors, the 10 processors will get a different value, each get a different value of iTask back, 0 through 9, and they do something different in each case. Well, okay, so we want to do 10 million trials, and we divide by the number of processors. So you're normally not going to know how many processors there are until you actually execute the program, because you may not even decide. You may want to run it with 5 processors one time and 10 another. So each processor says how many processors are there and which am I. And okay, if there's 10 processors, then we'll each do 1 million tests. Then each processor runs the same code here. Except notice that the seed for the random number generator, I passed in iTask because I want to make sure that each processor uses a different seed, therefore a different random number sequence. Because otherwise, if they all ran the same seed, they'd all be doing exactly the same experiment, and there's no point in doing 10 of them. Just you're going to get the same answer from each processor. So we get a different seed for each processor depending on what iTask is. And so at the end, everybody gets their average, says, okay, this is how much the option is worth in my million trials. And then we call this MPI. Well, actually, I said that this is MPI reduce, which means that only one processor gets the total. Normally, MPI all reduce, everybody puts in their average, and everybody gets back the sum of all the averages. See, this is n as 1, so this is just a scalar. So everybody calls MPI reduce and puts in their average of their million trials. And if this were all reduced, then everybody would get back the sum of all of those averages. But it's just reduced because we only need one processor to get the answer, and it can print it out. So this time we didn't use the all reduced, but it's essentially the same thing, except that everybody would get the answer. So then we take the final average is going to be the sum of everybody's average divided by the number of processors, and you print that out and you're done. So it's ideally suited for parallel processing, because the different processors can run their million tests each, and they don't need to communicate at all until the very end, and then only one number. Well, let's first see how we could parallelize the Gaussian elimination routine. That's the most important routine in the computational linear algebra book. And recall that Well, there's a 9 by 9 matrix. With Gauss elimination, we knock out the elements below the diagonal in the first column, then the second column, then the third column, so forth, and then we get it to upper triangular and do the back substitution. How could we parallelize this? Well, first thought, you might say, well, one processor can knock out everything in the first column, another processor can simultaneously knock out everything in the second column, and so forth, but that obviously won't work, because you simply can't knock out the elements in the second column until you finished with the first column, so those can't be done in parallel. However, when you're knocking out the elements in a given column, you can parallelize that. You could take a multiple of this and add it to that row, multiple of the third row and add it to the fourth on one processor, and multiple of the third row and add it to the fifth on another simultaneously. Or what we're going to do is basically parallelize the innermost do loop, and we're going to distribute the columns over the processor. So let's say there are 3 processors, and processor 0 gets the first column, processor 1 gets the second column, 2 gets the third column, then back to 0, 1, 2. So the columns are distributed over the processors, and processor 0 only keeps up with the first, fourth, seventh, etc. columns, and it doesn't do anything. It won't even know what's going on in the other columns. Well, let's suppose, so we're distributing the columns cyclically. There are other ways of parallelizing this, but this is the way we're going to do it. So, but now there's a special column that's called the active column. So you have to do the columns in order, but let's say we're up to the third column and we're trying to knock out everything below the diagonal in the third column. Well, this column is special. It's the active column, and the thing is, all the columns need to know what's in that column. All the processors need to know the active column, so they can keep up with, like processor 0 has columns 1, 4, and 7. Well, if 1 is already taken care of, so it's, but 4, 7, 10, etc. If it's a large matrix, that may be a lot of columns. When you take a multiple of the third row and add it to the fourth row, processor 0 can take that same multiple of its third row and add it to its fourth row in its columns, and processor 1 can do the same to its columns, and so they can distribute the work that way, and basically the innermost do loop is cut into 3 parts, each doing a third of it, and that will speed things up a great deal. However, the catch is that everybody needs to know the active column. See, in order to figure out what multiple of the third row to add to the fourth and what multiple of the third row to add to the fifth in its columns, it needs to know the active columns, because that's how you figure out what the multiples are. And in fact, when it goes to switching rows, it's got to know the active column, so it can figure out which rows to switch. So the special column, the active column, the one we're working on, knocking out everything below the diagonal, has to be known to everybody. So that's what's got to be communicated to all the processors. So here's how that is done. This is basically the LinyQ routine parallelized. You only make a relatively small number of changes, well, fair number. So everybody is running the same code, and they call this com rank to see which task number am I. So each processor knows what number it is. And okay, here's the column. This says look at all columns 1 through n, and I is the active column now, and that's what we're knocking out things in the column I, the outermost do loop. And JTask is the processor that owns the active column. It's mod I-1, NPES. If column 1, for example, that'll give 0, and that says, well, if it's first column, then JTask is 0, so processor 0 owns that. If it's column 2, PHYs 2, that's processor 1. The -1 there is because the processors are not numbered 1 through NPES. They're 0 through NPES -1. So anyway, this everybody knows who owns the active column. That's JTask. And then they say, well, am I JTask? Am I the one that has the active column? If so, then I need to copy that column, the ith column, to a vector, which I'll call column I, and pass that to everybody else, because everybody needs to know the active column. And then you call MPI broadcast, and processor number JTask, the one that actually owns it, will pass that vector to everybody else. So after this call here, everybody has the same vector column I, namely which will be the ith column from the one who knew what the ith column was, that owned it. And then we look at that, so everybody looks at column I, at the same active column, finds the biggest element, and switches the row I with the row that has the biggest potential pivot. And here we actually switch the ith row with the lth row, where L is the one that everybody determined, since they're all looking at the same active column now, that everybody determined is the one that has the largest element. So, but now notice that each processor only switches their columns. They switch their columns of rows I and L. And normally this would be 1 through N, but you only want to switch the ones that you own. You only want to keep up. So you're actually going to cut down on the work here. That's not so important because this is only order n square work. But anyway, each processor looks at columns I0 through N in increments of NPES. It's like MATLAB, except MATLAB puts the NPES between the two. So this means go from I0 to N in steps of NPES. So, but now here's the most confusing thing about this routine. What is I0? It's the, see, we don't want to switch the earlier columns because they're all just 0. There's no point in switching the portions of the lth row and the ith row before the active column because they're all 0. So we only want to switch from I through N. If you look at the original LINEQ, it goes I through N. But I0, we have to figure out which column is the first one that I own after I. So for example, processor 1 owns columns 2, 5, and 8. It doesn't want to bother switching the rows I and L in the column 2, only 5 and 8. So it needs to figure out, well, which column is the first one that I own after the active column, and it's 5, but how do you figure that out is the question. And it goes 5 and then goes up by increments of 3, 5, 8, 11, 14, up through N, and it stops once it gets past N. So this I0 is the first column after than or equal to, greater than or equal to I, that belongs to me. And there's a kind of a complicated calculation here that would take a while to explain, but I would just copy this here. If you want to try to figure it out, that's fine. But I would just copy these two lines here. You're going to be using them frequently, and trust me that that I0 is going to be the first column greater than or equal to I that belongs to processor ITask. And you do this calculation, and L0 is going to be an integer because L0 is integer. And notice that one thing for sure is that this I0 is going to be one of my columns because it's a multiple NPES plus ITask plus 1. So if ITask is 0, that's 1 plus some multiple NPES. If ITask is 2, it'd be 3 plus a multiple. So it's going to be one of my processors. But now what is L0? Basically, that's the number of blocks before I, and here's how you calculate it. It's using integer division here. This is, remember, a feature of Fortran that 3 divided by 5 is 0 if you do it in integer. If it 3 point divided by 5 point is 0.6, but 3 divided by 5 is 0, and 8 divided by 5 is 1. It rounds down, so that's important here. Anyway, just copy those two lines and trust that that's going to give you the column greater than or equal to I, the first column greater than or equal to I that belongs to me. So you don't want to switch all of your columns, just the ones that are after I and belong to you. And then here is where all the work is saved, because this is the only triple nested loop. Remember that if you took 5330 anyway, you'll know that the total amount of work is proportional to n cubed, because there's a triple nested do loop here. This is where all the work is done. That's what you want to, if you don't parallelize the most expensive portions of the program, then there's no point in it. So here's where you're actually taking the multiple of the ith row and adding it to the jth row, where j is I plus 1 through n. And so this needs to be parallelized. Well, it is, because each processor can take the multiple of the ith row and add it to the jth row, but only on their columns. So you see, if NPES is 10, then you're cutting the innermost do loop by a factor of 10. You only go through your columns. And here's this I0 again. That's the first column, so you don't want to process all of your columns, just the ones greater than or equal to I, because the ones before are 0. Same reason you don't want to switch them. So you go I0 through n. It's the same I0 as we just calculated. First column after greater than or equal to I that belongs to me, and then you go through n with increments of NPES, and that's where all the savings takes place. Now the back substitution is only order n square work, so it doesn't matter too much whether you parallelize that or not, but I do actually parallelize it with the back substitution. And when you're multiplying the dot product of the ith row with the known part of x, the sum of aij xj, that's you cut that by a factor of NPES also, because you only work on your columns. But then so each processor adds up their portion of this sum and passes it to MPI all reduce, and everybody gets back the total sum. See, n is 1. That means these are just scalars. So each processor adds up this sum in their column and passes it to MPI all reduce, and everybody gets back the sum of all the processors' sum i's. And so now they have the total sum, and then the processor that owns AII calculates XI and then broadcasts that to everybody. So this is only order n square work, so if you didn't parallelize that, it wouldn't make much difference. This is where the real gain is made. Well, if n is very large, which is what we're interested in, this should speed things up by a factor close to the number of processors, because the innermost do loop, where 99.9% of the work is done if you do it on a single processor, is split up. If you have 3 processors, this is a huge system, then when you take a multiple of this and add it to that in the innermost do loop, then each processor only does its columns, and so they're all working parallel and cutting the work by a factor of 3. And the message passing, see, you're only passing this one column, and each processor, if n is 1,000,000, is going to have 1,000,000 divided by 3 columns to work on, and only so it's going to be order n square work on each processor, and only has n elements to send or receive. So for large n, the ratio of the amount of work done on each processor to the amount of message passing is fairly large, so bigger n is, the more efficient this should be, the better you can take advantage of many processors. And so we actually did some tests here with a 2000 by 2000 matrix. With one processor, it took about 20 seconds to complete. Two processors, 10, cuts it by a factor of 2. Four processors, down to 5, everything's working fine. 8 processors, but notice that when you get down to 16 processors, there's not much of a gain. 32 processors, it actually gets worse. And that's unfortunately essentially always going to happen. As you get more and more processors, you've got more and more communication, and you're going to reach a point of where there's no gain in adding more processors. But if you go to a larger matrix, then you can go further out before it starts getting bad. Well, these results don't really prove that, do they? Well, here's another test where we went to even larger n, and there, you still reach a point of diminishing returns. Normally, if you make n larger and larger, you can use more processors before things start going bad on you. Well, the reason that you reach a point of diminishing returns as you add more processors is probably mainly the communication, but it's also due to something else. Even if you had no overhead from communicating, you're still going to have a limit because not all of the code is parallelized. In the routine we just saw, we did parallelize the back substitution, but let's suppose we didn't, then and only parallelize the forward elimination, then the order n cubed work is cut ideally by a factor of NPES, but the order n square work is not. And eventually, as you add more processors for given n, you reach a point of diminishing returns. And to see that, let's suppose that, this is just a general code. Let's say a general code requires t1 seconds to run using one processor. And let's say fp is the fraction of the calculations which can be parallelized, and the bigger n is, usually the fraction goes to 100%, but for any fixed n it won't be 100%. Then if t1 is the amount of time it takes to run in one processor, and fp is the percent of the fraction of the calculations that can be parallelized, then fp times t1 can be cut by a factor of NPES because that's parallelized. The other one minus fp isn't cut by a factor of NPES. So the amount of time on one processor divided by the number of time on NPES processors, that's the speed up ratio, is this. And if you divide out the t1s and multiply by NPES, you get this. And you see, as NPES goes to infinity, if fp is fixed, if n is fixed, and you use more and more processors, then this approaches the limit of 1 over 1 minus fp, and you can't ever get past that no matter how many processors you use. Well, basically if 1% of the calculations are parallelized, if 99% are parallelized, then it's that other 1% that you can't ever get more than a factor of 1 over a factor of more than 100, because you can't parallelize that 1%. This is called Amdahl's law. Now you may have noticed that in our PLI&EQ, the parallelized Gaussian elimination routine, everybody still stores the entire matrix. Each processor stores the entire matrix, even though each processor only works with its columns. They're distributed cyclically, and each processor never even looks at the other guy's columns, just its own. And so it cuts the computer time by a factor of close to NPES when n is large. But the memory is not, each processor is storing the whole matrix, which is unnecessary because it's not even looking at the other columns. So it's efficient PLINQ is efficient with regard to computer time, but not with respect to memory. If you want it to be efficient with respect to memory, then there's no reason for each processor storing the entire matrix. It can only store its columns. And all you have to do is go back to that routine. In fact, this is one of your homework problems. And everywhere you have an A of ij, you just replace that by A of I and then j minus 1 over NPES plus 1. That will pick out that will be the number of the column of your local version. In other words, if each processor only stores its columns, then see if j is 1, let's say NPES is 10, and j is 1, this will be 1. In fact, if j is anything between 0 and 9, 1 and 10. So if the first 10 columns, j is 1 through 10, this divided by 10 will be 0. So it's integer division here. That'll just truncate down to 0, and that will be your first column. So every processor, the column in the first 10 columns, the one it owns in the first 10 columns will be column number 1, and then the one it owns in the next 10 columns will be column 2, because if j is 11 through 20, then j minus 1 over 10 will be 1, so this will be 2, and so forth. So all you have to do is replace the column number by this. That's doing integer division. And then each processor will not store the entire matrix. It'll only store n by this. So basically, this is the largest value of j, and so it's going to cut the amount of memory in each processor by a factor of NPES. So in fact, here's a routine where PLINEQ is efficient with regard to memory as well as computer time. And notice the matrix is stored n comma star. That means this routine doesn't need to know how many columns there are, and it does need to know how many rows, but in the main program that calls it, that will be dimensioned accordingly. But it's assuming then that each processor only passes its columns to the routine, which is why we didn't do this in the original version, because it makes things more complicated, but it's more efficient. And then everywhere in the routine that we refer to A of I comma j, well, here's A of L comma k in the original, and k is replaced by k minus 1 divided by NPES plus 1. So L comma k would be the element if each processor stored the entire matrix, but L comma KME, that KME, k is replaced by k minus 1 divided by NPES plus 1. So the first column that it owns will be KME1B1, and the second column that it owns, for example, the processor 1 owns columns 2, 5, and 8. So column 2 will be 1, column 5 will be 2, column 8 will be 3, and so forth. So basically all you have to do is go through the routine and replace every call to A. Here's the innermost loop here, and this was A of j comma k, A of I comma k. K is replaced by k minus 1 divided by NPES plus 1. So it's fairly straightforward to convert it to be efficient with regard to memory. Okay, this idea can also be applied to a band matrix. In fact, PD2D has a parallel band solver, and it basically uses what we've been talking about here, but applied to a band matrix. And so it takes advantage of the band structure and the number of processors. So again, assuming we have 3 processors, and this is the active column, then processor number 3 owns this column, this column, this column, this and that. So it only keeps up with those. It won't store the entire matrix. PD2D is efficient not only with regard to computer time but memory with the parallel solver. So each processor has the processor that owns the active column, which in this case would be processor number 2. Well, I'm numbering them 1, 2, and 3. They're really going to be called 0, 1, and 2. But anyway, processor 2 owns the active column, broadcasts it to everybody, and everybody, for example, processor 3 now knows which rows to switch and what multiples of the ith row to add to the others, and it only does it to its column, so it cuts the work by a factor of 3 and takes advantage of the bandwidth. Well, you might ask, why are the processors, the columns distributed cyclically over the processors? Why not just, if you have 10 processors and n is 100, or well, let's say n is 1,000, and you have 10 processors, then why not just have the first 100 columns belong to processor 0 and the next 100 processor 1 and so forth? That would be simpler, wouldn't it? Well, in fact, it would be a little simpler. Here's a routine where the Gaussian elimination, the columns are distributed by blocks. So here, if there are n columns, and we're assuming in this routine assumes that n is a multiple of NPES, keep it simple. So say n is 1,000 and there are 10 processors, then NB is the number of blocks, number of columns for each processor would be 100. So each of the 10 processors gets 100 columns, but instead of getting columns 1, 11, 21, 31, so forth, processor 1 gets columns 1 through 100, and processor 2 gets columns 101 through 200 and so forth. And that actually does simplify things a little bit. Then if the active column is I, the processor that owns that, all you have to do is divide by the number of columns in each block, well, I minus 1, and you get the processor that owns that column. And more importantly, it still has to, whoever owns the active column will still have to broadcast it to everybody, but it's a little simpler. The limits of, which columns do I own? If I'm processor I task, which columns do I own? Well, that's pretty easy. Just I task times the number NB, which is 100 in our example, plus 1, through I task times 100. So again, if the example is if you have 1,000, if n is 1,000, 1,000 by 1,000 matrix, and you have 10 processors, then each processor is going to get 100 columns. But instead of doing them cyclically, if the first 100 belong to processor 0 and so forth, then if you want to know which columns do I own, it'll be I task times 100 plus 1 up through I task times 100. 1 through 100 for processor 0, 101 through 200 processor 2, and so forth at processor 1. And then you can just take the maximum of I in that, and you make sure you get the one greater than or equal to I. So it is a little easier, but it's not as efficient. Now, why? So why distribute the columns cyclically? Why not just, if you have n is 9 and you have 3 processors, why not just give the first 3 columns to processor 0, the next 3 to processor 1, the next 3 to processor 2? Well, the reason is it's not as efficient because, see, by the time you get halfway through the matrix, then the first processors are no longer have anything to do because they don't own any columns. All their columns are finished. And as you go through the matrix, fewer and fewer processors have anything to do. And remember, the total amount of work is going to be 1/3 n cubed multiplications for large n, no matter how you distribute the work, and so the total amount of work is the same, and so the faster you're going to get through, you're going to get through faster if you distribute it evenly among the processors, and that's what happens if you distribute them cyclically, because at any point, no matter where the active column is, for a large matrix here, all the processors have about the same number of columns left to work on, whereas if you do them by blocks, then halfway through the first half of the processors are finished and the last processors are doing all the work, and so it's got to take more time, and it does. So that's why you distribute them cyclically, because you want all the processors to do about the same amount of work. If you've got a fixed amount of work to do, then the more evenly you distribute, the sooner you'll be finished. Okay, I also have a routine in the book that's a parallel version of an iterative linear system solver, and this is very different. We assume that the matrix is stored in sparse matrix form, that is, that there are NZ non-zero elements in the matrix, so it's not stored as an n by n matrix. Only the non-zeros are stored, and let's say they're NZ non-zeros. Then A of 1 is the value of the non-zero element in row I row of 1, J col of 1. So A I row and J column are vectors of dimension nz, and they contain the values of the non-zeros and the corresponding row and column. And this iterative solver, and the one you're going to use, Jacobi method, the most work where a large percentage of the work is done is in multiplying a matrix times a vector. So let's say you want to multiply the whole matrix by Pn. Well, if you can break that matrix up into, say you have 10 processors to 10 parts, so each processor only knows 1/10 of the non-zeros, so its A and I row and J column, and its NZ will only be part of the matrix. It doesn't know about the other part, but they'll all get together, and the entire matrix A is the sum of these little matrices, each of which is broken into the non-zero parts. And where most of the work is done in this routine, this iterative solver, it's multiplying the entire matrix A times some vector P, and each processor only knows part of the matrix, but that's okay. It will basically multiply its part of A times P. This is API of A of IZ is the non-zero of A in row I row of IZ, comma, column J col of IZ. So you multiply A of IJ times PJ, and you end up with this API, which is basically its part of the matrix, the part that it knows that was sent to it, times P, and then you just add those vectors up. So everybody puts in their matrix times P, and they all reduce, adds them all up, so everybody gets back AP, which is now the entire matrix times P. And so if all the work was done there, that would cut the work by a factor of approximately NPE at number of processors, because each processor only does 1/10 of the work if there are 10 processors, because it only has to multiply, it only has 1/10 of the non-zeros. Well, there is some other work here that's not completely negligible, but it's also distributed over the processors. And then there's a test program in here that you're going to be using to test this parallelized iterative solver. And it sets up a finite difference matrix, which is sparse, mostly 0 elements. And it looks like the parallelized iterative method doesn't really care how the elements are distributed, as long as they're distributed more or less evenly among the processors. But we actually distribute them by columns again, so this is a sparse matrix, but each processor is only going to own the non-zero elements in its columns, and the columns are distributed cyclically again, so the same as before, except that we don't store each processor doesn't store the entire matrix or even the entire matrix of its columns, just the non-zeros, but it'll store the non-zeros corresponding to its columns, and there's a reason for that. But it looks like it doesn't matter. So basically you go through and you generate all the non-zeros. This finite difference matrix, so all the non-zeros are going to be 6s and minus 1s. It checks to see if the element is in column L, then it says who owns column L, and if it's me, then I'll save my elements. If it's not, I'll just ignore it. And in the end, AS will be the non-zero elements corresponding to my columns only. So each processor, if I'm processor I task, AS will not be the entire, not all the non-zeros, only the non-zeros in my columns, and the I row and J col will be the corresponding row and column of that element. So these will all be L's here. These will all be my columns. And you pass it to PCG, and then PCG puts them together and solves the problem. You're going to be using this to test your iterative solver and your Gaussian elimination routine. For the Gaussian elimination routine, you basically have to copy the sparse matrix onto a full matrix. So at this point you'll have to copy. You'll only have access to the non-zeros in your columns, and you copy those to your columns of a full matrix and then call the PLINEQ. So you can use this testing routine, and the solution that's given in the book. You can test your iterative solver in problem 1 and your Gaussian elimination solver if you copy your portion of the sparse matrix to your portion of the full matrix. There are also routines in Chapter 6 to parallelize linear programming simplex method, but it's kind of similar to the Gaussian elimination routine, because the innermost do loop, where the vast majority of the computer time spent for large problems is just like Gaussian elimination, is adding a multiple of one row to another. And again, you distribute the columns cyclically and only do your columns, and that cuts the work and pretty efficiently. Here are some results for the linear programming simplex routine that's parallelized. Increase the number of processors from 1 to 4, and it cuts the work by close to 4. But as always, there's a point of diminishing return. From 8 to 16 processors, no gain. Presumably, if you solved a larger problem, you could use 16 processors efficiently, and so forth.